Yeah, so the midterm will be this Friday, and it will just cover chapters 1 through 4. Today we are going to start chapter 5. Chapter 5 will not be on the midterm. I know many of you are asking, what is going to be on the midterm, and I don't have a good answer for that, other than I would say study the lecture notes, make sure you can do all of your homework problems. In my opinion, the midterm is very fair, but of course I would think that. But I'm not writing it to try to trap you guys or anything, okay? But pay attention to your answer choices, because some of them will look and sound similar, but only one will be correct. So anyway, so we'll get started. Chapter 5. Okay, and chapter 5 is on probability. Okay, so we can think of probability. It tells us how likely.
Professor, can you make it darker?
Oh yeah, I keep forgetting that. Thank you. So we'll start over. Okay. So how do I do this? No. Okay. Probability tells us how likely or unlikely an event is to occur. Okay, and before we can really get into probability, we should talk about the meaning of randomness. Okay, and so random means unpredictable, and showing no pattern. Okay. However, things that are random are not necessarily impossible to understand. Okay, we can still understand, still come to understand random events. Okay, so for example, a coin flip is random, okay? No one can predict the outcome of a coin flip. Okay, so we cannot predict the outcome of a particular coin flip. And a sequence of coin flips will not show any kind of discernible pattern. However, we can still say things like the probability that a coin will land heads is 1/2 or 0.5. Okay, but we can still Okay, and so that is, so we can still understand kind of the nature of coin flips, even though any individual coin flip is unpredictable. All right. Okay, and so as we talk about probability, we should differentiate between theoretic probabilities and empirical probabilities. Okay, so I've got and so we'll talk about theoretic probabilities first, okay? And so in our course, we will take on what's known as the frequentist view of probability, okay? So we will take on, we will use the, so let me just kind of draw a vertical line. We will use the frequentist view of probability. Okay. The other view of probability that exists would be the versus the Bayesian or Bayesian view. We're only going to concern ourselves with the frequentist view of probability. And so our notion of probability, the probability is defined as the long-run relative frequency. Okay, long run meaning approaching infinity. Okay, so, you know, when we say the coin has a probability of 1/2 of landing on heads, that means after close to an infinite number of coin flips, the relative frequency of heads is going to be 1/2. Okay, but of course we can't achieve that. You know, a lot of times theoretic probabilities are determined by mathematical rules and formulas. I'm sorry, are you having a hard time reading something I wrote up there? Yeah, okay. After long? It says long run. So I apologize for my... okay, no problem. Okay, so long run means approaching infinity. And so theoretic probabilities, these are determined by math rules and stuff like that, okay? So for example, when we say a coin will land heads, so example of theoretic probabilities, we say the probability that the coin lands heads is equal to 0.5. This is a theoretic probability. We're saying, you know, the coin has two sides to it. Both sides are equally likely. Therefore, it should land heads 1/2 of the time. And if we were to repeatedly flip the coin millions and millions, approaching an infinite number of times, we would expect to see a relative frequency of 0.5. Empirical probability, on the other hand, these are based on actual experimental trials or simulations. Okay, so for example, let's say you've never seen a coin before, you don't have an understanding of physics, and somebody says, what's the probability that a coin will land on heads. Okay, so imagine. Okay, so maybe we are an alien. We've never seen a coin before. Okay, and we do not understand physics. Who does anyway, right? Newtonian physics, maybe we can understand, but then at like the quantum level, it's like humana. Okay, we got people who understand it. So never seen a coin before. We don't understand physics. What is the probability a coin lands heads? Okay, well, the way we're going to do this is we're going to take a coin and we're going to just start flipping it. Okay, so maybe we flip the coin 1,000 times. So we do a trial. Okay, so experiment time. Flip a coin 1,000 times. Okay, and we count 491 heads. Okay, so our empirical probability is equal to 0.491. Okay, and so basically, if we had to report back to the alien motherland, we would say, well, I don't know how coins work, but if I had to predict the probability that a coin lands heads based on these other times I've done it, I'm thinking it will land heads with probability something around 0.491. Okay, so this is, we anticipate that, so we would say, we predict that the coin will land heads with probability 0.491, and this is based on our experimental data. Okay, and this is still very useful. I mean, for something like a coin flip, it seems silly because we understand the math behind a coin flip. We can say, oh, two sides equally likely, 1/2. No big deal there. Okay, but a lot of times there are just much more complicated things. Okay, so if you ever watch, if you ever follow sports and you go on like ESPN or whatever, and they have some upcoming game, they'll say, this team has a probability of winning with this percentage. Okay, so I think, recently I saw something, it was like, who would win, the 95-96 Bulls or the 2015-2016 Warriors, right? And then what they did was, there's no mathematical formula in of itself where you say, oh, I've got Michael Jordan, and here over here I got Steph Curry, and we're going to have them play against each other. But we can kind of create these, based on our understanding, we can create simulations that use the math that we do understand, and we can have the computer kind of play games against itself, all right? And anybody who has a sports game has seen the computer play games against itself, and you can just have the computer play 1,000 games against itself or 10,000 games against itself. Okay, and maybe in the 1,000 games, one team wins with 60% of the time. Okay, and then we'd say, okay, when we say this team has a probability of winning of 60%, it's essentially the result of a bunch of simulations. Okay, we're not, and so of course, if our simulations are no good, then our predictions are going to be poor. But that's a whole field of study out there. Is how do we improve these computer simulations for whatever it is that we're trying to do. Okay, something as quote, what's important in life, So maybe sports is not super important in terms of scientific discovery, but it sure is profitable, and so a lot of money is being poured into sports simulations because that's a well, for some people, an important venture. And I'm not above sports. I love following it, but we're not going to be I don't know, changing? Okay, it doesn't matter. All right. So anyway, empirical probabilities, it's still something we do, okay? And so actually I get to teach an upper division class that's on computational statistics, which kind of enters this realm of setting up computer simulations for stuff, okay? As far as this intro class goes, we're going to learn some of the basic rules for theoretic probabilities, okay? Okay, so let's, oh, and then there's one more thing, and that is the law of large numbers. Okay, and the law of large numbers basically says that as you perform more and more experimental trials, okay, the empirical probability that we observe should approach the theoretic probability. Okay, and so as far as casinos stay in business because of the law of large numbers, insurance companies stay in business because of the law of large numbers. In any specific sequence, the player might actually come out ahead and win money, and the casino would lose money. Okay, but in the grand scheme of things, if thousands of people are playing, and and they're open, 24 hours a day and whatnot, and there lots of these little experiments are happening, in the long run, the casino will come out ahead because all of the games are designed in such a way to give the house an edge. Okay, insurance premiums are calculated in such a way that over the course of time, the insurance company is profitable. Okay, it's not, and this is, insurance companies are not unethical for calculating their premiums this way. They offer a much needed service so that people can survive unforeseen circumstances, but they are certainly calculated in a way so that they can remain open for business, okay? And so, sure, one person might get into a bunch of car accidents and cost the insurance company, hundreds of thousands of dollars in payouts, but overall, if everyone's paying their premiums, they still come out ahead. So that's the law of large numbers, of course. But in any given circumstance, because of randomness, we can't predict the outcome. We don't know what's going to happen, and no patterns will necessarily emerge. Okay, so let's talk about some of the basic rules of determining probability. Okay, so basic probability rules. Okay, so we have simple outcomes. Okay, so simple outcomes mean every outcome has an equal chance of occurring. Okay, so as far as simple outcomes go, so certain things are simple outcomes, other things are not simple outcomes, okay? All right, and so, but when we are dealing with simple outcomes, we can say the probability that some event A happens is going to equal to the number of simple outcomes in A divided by the total number of possible outcomes. Okay, so the coin flip probability that a coin lands heads is an example of simple outcomes. Okay, we have two simple outcomes. Both are equally likely. We have heads and tails. Okay, so the probability that the coin lands heads is going to be 1 out of 2. We have two possible outcomes. Only one of them counts as heads. So there you go. Good with everybody? I think this is easy. All right, so here I'm showing a deck of cards. Okay, this is all 52 cards in a deck. Okay, and let me see. Let me make this a tiny bit smaller. Okay, so these are clubs, these are spades, hearts, and diamonds. Okay, and then these are ace to all the way up through 10, jack, queen, king. Okay. All right, so this will be your first clicker question. If I pick a card at random, what is the probability it will, okay, so I'm going to figure that part out for, next. I'm going to write down your answer choices. So your answer choices will be 1 out of 52, 13 out of 52, 4 out of 52, 12 out of 52, 26 out of 52. Okay, what is the probability that it will be a diamond? Okay, so go ahead and clickety click. All right, so this should be easy. Okay, yeah, everybody, so far so good, looking at my screen here. Okay, so we'll say 10 more seconds to get your clicks in. Okay, and I'm going to hit call time right here. Wait, I just lost my mouse cursor. Yeah, oh, here it is. Okay, so time. All right. Okay, everybody. Somebody got it wrong. Okay. And that is the correct answer. Okay. So yes, there are 13 diamonds. So we have, this would be equivalent to 1 out of 4. So if we select a card at random, the probability that it is a diamond is 13 out of 52. Simple enough. Okay. All right. So we're going to move on here, and we have the concept of and or. Okay, and so first we'll talk about or events. Okay, so when we use the word or in English, there's an ambiguity to the use of the word or. Okay, so for example, I'm going to ask you a question here. I'll ask you the same question twice. And I think your answers will change even though I'm using the exact same words. Okay, so I could say do you like chocolate or vanilla ice cream? And you would tell me, I like chocolate ice cream, or I like vanilla ice cream, or something like that, right? Okay. I'm going to use the exact same words, ask the exact same question, but your response will be different, okay? I could say, do you like chocolate or vanilla ice cream? And your answer would be yes. Or no, if you hated ice cream for whatever reason. But so there is an ambiguity in English, okay? And so in statistics, when we use the word or, it's always the latter, okay? It's an inclusive, or what we call an and or, okay? So this is an inclusive or the also known as the and or, okay? So when we say, do you like chocolate or vanilla ice cream? That means, do you like chocolate ice cream? Do you like vanilla ice cream? Or do you like both chocolate and vanilla ice cream? It's if you like either chocolate or vanilla ice cream, your answer is yes, okay? And so that's what we mean here, okay? So basically when we say the probability of A or B, this is the probability that A happens, or the probability that B happens, or that both happen, okay? So this is probability of A happening, or B happens, or both happens, or both happen. Okay? And the way we calculate the probability of A or B is going to be equal to the probability of A plus the probability of B minus the probability of overlap, A and B, okay? So it's going to be the probability of A plus the probability of B minus the probability of A and B. And so often we draw little Venn diagrams because maybe they help for some. These are the best circles I can draw, okay? So A or B is this this shape here, okay? Don't laugh. Be mature. All right. So A, and what it is it's A plus B minus whatever this thing is, okay? The overlap, A and B, okay? Because if I did A by itself and B and I didn't subtract off the overlap, I would have too much, okay? And so I have to subtract off the overlap, at least, just one time there, okay? Okay, is that good? All right, so then let's try another question here. All right, let's. Okay, so this is again clubs. I should have copied this last time. Spades, hearts, and diamonds. Okay. All right, so I'm going to say I pick a card at random. Okay, what is the probability that it is a 4 or a spade? Okay, and your answer choices are okay. So okay, so we'll say just a few more seconds here. Get your clicks in. 3, 2, 1. Click, click, click. Okay, let's see how we did. That is the correct answer. Answer choice C. Okay. All right, so let's see what happened here. Okay, so we can just look at. I mean, when we have all the cards on the screen, we can just kind of circle the ones that qualify. So these all qualify. All of the spades qualify. Okay. So I've got 13 that count here, and then I count these 14, 15, and 16. These are all 4s, so those all count, and we see, okay, we got 16 out of 52. So that's good. Okay. We could also do it. We can say, okay, well, this is the probability of 4 or spade. Okay. And so if we, I'm going to go ahead and just delete. Whoops, that is not what I wanted to do. I'm going to just delete these answer choices to give myself some room here. Okay, so we can say, well, probability of 4 or spade is going to equal the probability of 4 plus probability of a spade minus the probability of overlap, 4 and spade. Okay, so the probability of a 4, there are 4 out of 52 that are the number 4. Probability of a spade, there are 13 out of 52 that are spades. And how many 4s and spades are there? There's only one. Okay, there's only one card that is 1 out of 52. And so if we add these up, we would also get 16 out of 52. Okay, so there you have that. Good? Okay. Okay. Okay, we can let's try something else out. Okay, so I'm going to say we surveyed 200 people. Okay, and we're going to say 90 own a dog. We'll say 70 own a cat, and we'll say 30 own both cat and dog. Okay, and so I'll ask you a question. What is the probability? Yes.
That doesn't add up to 200.
That's okay. That's okay, yeah. What is the probability a randomly, so if I'm going to randomly select someone out of this group of 200, okay? So what is the probability a randomly selected person has a cat or a dog? Okay, and these will be your answer choices. So this will be another clicker thing here. So we'll say 0.45, 0.35, 0.15, 0.8, 0.65. Oh, you know what? Let me change one of these to 0.95. Okay, so go ahead and crunch, crunch, crunch. So again, we're randomly selecting out of this group of 200. Okay, so we'll say 10 seconds. 5 seconds. 3, 2, 1. Okay. Let's see. And that is correct. E is correct. Okay, so let's see. So what we want, so we've got probability of cat or dog. Okay, and so just kind of using what we learned in the formula, probability of cat plus probability of dog minus probability of cat and dog. Okay, so the cat, we have 70 out of 200 people have a cat. For the dogs, 90 out of 200 people have a dog. And then we're going to subtract off the overlap where 30 out of 200 people have both a cat and a dog. Okay, and so this gives us a total of 130 out of 200, which gives us 0.65. Okay. Is that good with everybody? Okay. We can also complicate the questions, and I won't make a clicker question out of this, but so using the same information that I've given you, okay, I could ask other questions such as, so you know, I pick a person at random. Happens to the best of us. So what is the probability this person okay, we'll say has a dog and no cat. So this will be A, and then B will be has a cat and no dog. And C will be has neither cat nor dog. Okay. All right, well, to answer something like this, we can build ourselves a little table, okay? And this is a handy little tool. Tables are very handy, okay? And we will say, okay, well, you can have a dog, and the complement of having a dog will be or not, okay? This is, the entire world is split into people who have dogs and people who don't have dogs. That's it, okay? And the entire world can also be split into those who have cats and those who don't have cats. There's no other person out there, okay? And we have a total of 200 people, okay? How many people own dogs in total? 90, right? How many people own cats in total? 70. And then how many have both cats and dogs? 30, okay? So these are the bits of information that are given in the table. Everything else can be filled in because we can do math, right? So if 70 goes here, what number has to go here? 130, right? And what number has to go in this no dog total column? 110, okay? And if 30 goes here and these two numbers add up to 70, we know this number has to be 40, and we know this number has to be 60, and we know this number has to be 70, right? So all of these numbers fill in for us, okay? And because of that, and now that we've filled out our table, we can answer A, B, and C quite easily. So has a dog and no cat. What's that? 60 out of 200, 0.3. Has a cat and no dog. 40 out of 200, so that's a 0.2 probability. And has neither cat nor dog. Okay. Good? I hope. All right. Well. Okay. And with our last bit, let me talk about this. Wait, does everyone have this written down? Are there any questions on this? We're all good? Okay. So I mean, you only have to be given these bits of information and you can fill out everything else, okay? Okay, so now we also have mutually exclusive events. All right, what does it mean to be mutually exclusive? All right, so if A and B are mutually exclusive, it means that if A happens, B is impossible, or B will not happen. And if B happens, A will not happen. Or in other words, if one happens, the other is impossible. So we can say the probability of A and B is going to equal what? 0. Okay? So if one happens, the other is impossible. Okay? And so, if we think back to, so I'll say recall the rule that we just learned earlier, probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? And if A and B are mutually exclusive, okay, then what's going to happen is that the probability of A and B become 0. Okay? And so this simplifies to the probability of A or B is equal to the probability of A plus the probability of B. Is that okay? This brings up also an important concept that I need to also say in our last 1 minute of class, okay? All right, and that is complements. So I just want to make sure everyone's got this down. It'll be posted. Okay, so we have complements. Okay, so complements spelled with an E, not I. Complement with an I is a nice thing you say. Complement, so complement of an event is the event that it does not occur. Complement of event A is the event where A does not happen. Okay, so we can say A complement can also be written as not A, and the probability of not A is equal to 1 minus the probability of A. Okay? And then I think this is kind of just implied, but maybe I'll explicitly say that. All probabilities we observe must be between 0 and 1. And 1, inclusive. So if you ever get a value bigger than 1 or smaller than 0, you've done something wrong. Okay? Okay, that wraps up today. We'll see you guys on Wednesday. So again, no office hours today, but I do have office hours tomorrow. I think you guys should have gotten an email from me about that.